Hey there! In this video, I'm going to continue the discussion on bouncing particles and ideal gases as we build up to the conclusion that I'm showing in the box there. Alright, so from part 1, we determined that if we took a particle, a single particle, and we put it in a box with some speed vx, then we could find the time averaged force on the wall as follows: mvx squared over L. For our second problem, we go ahead and we put two particles in the box. And we give them each a different speed now. We're not exactly sure what those speeds are. I've labeled them Vx1 and Vx2. The particles can collide with each other through elastic collisions, so they can bounce off. And we want to find the time averaged force on the walls again. Same goal. We've just upped the complexity a little bit. So, the first thing that we need to make clear is what an elastic collision is like when we have two particles of equal masses. And I'm not going to prove everything mathematically. I'm going to show some things in a simulator for the sake of time. However, you can do these calculations very easily yourself. So if I have two particles, this one has a speed of 1 meters per second, and this has a speed of 1/2 meters per second, and I shoot them at each other, when they collide elastically, they trade velocities. That's the first thing that we want to make very clear, is that we have a trading of velocities when two particles of equal mass collide with each other elastically. Alright, so I'll go ahead and make a note. So this elastic collisions point really translates to when the particles hit each other, they trade velocities. Okay, let's go ahead and use this simulator here to conduct a bit of an experiment so that we can kind of brute force our way to seeing some useful conclusions. And then from there, we'll describe things mathematically. So I just put my second particle in a random spot. My first particle is on the wall. And if I were to hit play here, I would find that my second particle collides after 3.65 seconds. Okay? Let's say that I took this particle and I moved it to a new spot. Is that going to change the time for it to hit that wall? Interestingly enough, it doesn't when we change the speed. Or the location, I mean. Now let's go ahead and change the speed a bit. I don't know, something like that. How about? Let me hit the play button. Particle 1 hits particle 2. And now particle 2 hits the wall at 3.65 seconds. We still get the exact same time. That's really interesting. Let's go ahead and take this particle and put it close to the wall, right? So it hits the wall faster, but watch this. Now, we get that momentum transfer, and the second particle hits the wall a second time, but in that same time chunk of 3.65 seconds. So for the velocities to swap and for the collision to happen, it always takes like 3.64, 3.65 seconds. It takes the same amount of time. Right? And I could go like this again. Momentum's transfer. And the collision on the right wall, 3.65 seconds. That's going to be extremely important to find out what that time chunk is. Because basically what we can do is we can see how things reset every other 3.65 seconds. What do I mean by that? Well, let's continue playing this. Okay, now watch the left wall, and let's just keep going. Focus on the left wall. And now you can see that particle 1 took another 3.65 seconds to basically reset to having its original velocity and it being on the left wall. So now, if I'm here again, and I were to ask you how long would it take for this particle 2 to get hit, have a speed of 1, and go and hit that right wall, you would know now immediately that it's going to be 3.65 seconds. And watch that. And bam. Another 3.65, 3.64 seconds went by, somewhere around there. And now you know again that for this to reset, for this ball here to get its speed of 1 meters per second and to be back fixed at the left wall, it's going to take another 3.65 seconds. And bam. Okay? So hopefully now we've taken this complicated problem and broken it down into discrete, basically time chunks that are going to be very helpful in analyzing this problem. So our next goal is to figure out what one of those time chunks is. So now let's go ahead and try to describe what's going on mathematically. I'm going to go ahead and draw my box again. And I'm going to go ahead and put my x-axis here, let's just say. And I'm going to put one particle on the left wall. So there's particle 1. And I'm going to go ahead and label a random spot on here. We'll call this spot x1. And I'm going to place particle 2 on x1. So here's particle 1, here's particle 2. And I'm going to give each of these some velocity, vx1 and vx2. All right, so what's going to happen? If we just go ahead and play our simulation, these particles are going to meet up. This first particle on the left here is going to catch up to this second one here, and they're going to meet at some further position. So that's the first point that I want to illustrate, and I'm going to call this, after some change in time, delta t1. Okay, so in this picture, some time has gone by. These particles have collided with each other at a new location, x2. And remember, they've traded velocities because of the elastic collision. So particle 2 now has the speed vx1. All right. And then to complete this series of events, I guess, then we're going to wrap this up by having another change in time, delta t2. And so for our last picture, we have that our ball on the right, particle 2, has gone in and slammed into the right wall with a speed vx1. All right. And now our goal is to find the change in time for this entire process. So I'm going to call this delta t equals delta t1 plus delta t2. And we want to figure out what delta t is. And you can replicate these calculations for various x1 positions, and you'll get the same delta t regardless. I could change the velocity of this particle, and I'd still get the same delta t for these cycles. Okay? If you're not convinced by me, you can go ahead and try some of those calculations yourself. I'm going to do it for this sequence of events. Okay. So now that we're here, let's go ahead and just make some velocity statements. So first off, we know that vx1, based on these first two pictures, vx1 equals my change in displacement. It's going to go to x2 and it starts at x equals 0. So x2 minus 0 over delta t1. And we also know that my second particle, particle 2, is going to have a speed vx2. And it's going to have a displacement of x2 minus x1 over the same change in time, delta t1. All right, for this second event here, if I have my particle 2 starting at position x2 and it has speed at x1, if our box has a side length of L, we get that v x1 equals our final position L minus our initial position x2 over delta t2. And so we have 1, 2, 3, 4 equations here. And we could very easily go through and solve for delta t, do this all by hand. Instead, I'm going to go ahead and just plug these into Mathematica and have it do it for me to save time. Okay, so right now I'm in Mathematica, and I went ahead and just plugged in our exact equations from before. And if I go ahead and solve this system of equations, I can get that my total change in time t is L over Vx1. All right, so let's go ahead and note that my total change in time from this system of equations, delta t equals Vx1, or sorry, L over Vx1. Right? There we go. So this is our first important conclusion. And again, you can break this these collisions up into these little time chunks, L over Vx1, no matter what the situation is. If you're not convinced by me doing it this way, you can create more scenarios in your own head and do it, or you can go ahead and watch the simulation here, right? And you're going to keep getting that same time interval of 3.64 seconds because you effectively have L, which is 3.64 meters if you account for the sizes of the balls, divided by the initial speed of this ball on the left, which is 1 meter per second. That's what's happening. Right? Show that again. .64 seconds. All right. Now that we're completely good on that, we have to consider the two different situations that can happen. Now, even though I can break this process into time chunks of L over Vx1, the same events aren't necessarily going to happen in each of those time chunks. So what do I mean by that? Let's say that I took this particle and I dragged it over here and I hit play. One collision happens after 3.64 seconds. If I dragged the particle further away and hit play, one collision, two collisions happen after 3.64 seconds with the right wall. Okay, so let's go ahead and just make a note of that real quick. So in our simulation, we saw that two different scenarios could occur with a time chunk of L over Vx1. And in the first situation, we had a single collision with a momentum transfer of Vx of 2mvx1. And then situation 2 was we had two collisions with momentum transfers of 2mvx2 and 2mvx1. Let's see that one more time. Here, 2mvx2, there's that collision. And then bam, here's 2mvx1. So this was the two collision scenario. If I drag the particle further back, we have here a single 2mvx1 collision. If I change the direction of the velocity, it does not matter. I play the animation again. This is just another situation where you get a 2mvx1 collision with the right wall. Okay. Now we got to figure out when does situation 1 happen and when does situation 2 happen, right? And your intuition should probably tell you that the location of this second particle is what's going to determine that, right? If I dragged the particle far enough back, then you could get the situation where you have one transfer of momentum. If I put it super close to the wall, it could slam into it, and then particle 1 would hit it, and then it would slam into it again, right? But we gotta find what that distance is. So that's the next goal here. So determining situation 1 versus 2. Okay, let's go ahead and draw our picture. Actually, let's go ahead and just use this guy right here. Now, I'm going to define two different possible times here. Let's go ahead and call something delta t, let's go ahead and call something delta tw. This here is the time it takes for particle 2 moving at Vx2 to hit the right wall. Right? Imagine that I covered up this particle over here. If I just let this go, this particle here would hit the wall over a certain amount of time. I'm going to call that delta tw. Okay? And now I'm going to define another time, delta t12. This is the time it takes for particle 1, maybe I should put a comma here, there we go, for particle 1 to hit particle 2. Right? If I let this go, particle 1 would hit particle 2, eventually. I could even get rid of this wall. Particle 1 would probably hit particle 2. Of course, if particle 2 was moving faster than particle 1, they would never hit each other. So this time wouldn't even be a thing, right? So the key thing that we need to figure out here is, when is delta TW less than delta T1, 2? If this is the case, then 2 collisions happen. Okay, I just made a lot of claims, so let's break that down. So when delta TW is less than delta T1, 2, that means that this particle here is going to collide into the right wall faster than the time that it would take for 1 and 2 to hit each other. So this second particle is definitely going to hit the right wall on itself, or by itself. And then it's going to bounce back, hit into the first particle, and then hit the wall again. And we're going to get 2 collisions happening. All right? If delta T1, 2 is larger than delta TW, then the opposite happens. Then this particle is definitely going to hit particle 2, and then particle 2 is going to slam into the right wall once. And we get 1 momentum transfer. All right? So now we need to find out the position x1 when this happens. So let's go ahead and ask, what is delta TW and what is delta T1, 2? So delta TW, actually let's just use the definitions of speed here. So we can say that Vx2 equals, if it ends at position L, then this would be L minus x1 over delta TW. And so therefore, delta TW equals L minus x1 over Vx2. Okay? The next question I have to ask is, what is the longest possible time for delta T1, 2, right? The longest time that it could take for particle 1 to hit particle 2 is if particle 1 had to travel the entire length of the box, right? Right before slamming into particle 2. So if it had to travel this entire length of the box, that would maximize delta T1, 2. Okay? So with this in mind, Vx1 equals L minus our initial position, 0, over delta T1, 2. I could even call this like max or something, but I'm not going to. All right, let's just keep this easy with our notation. And so we get that delta T1, 2 equals L over Vx1 when it's maxed out, right? So if delta TW is less than this, we're going to get 2 collisions that happen. So let's just go ahead and plug these guys in. We get L minus x1 over Vx2 is less than L over Vx1. And now we just need to solve for x1. L minus x1 is less than L times x2 over Vx1. And so x1 is greater than L minus L Vx2 over Vx1. We could simplify this as x1 is greater than L times 1 minus Vx2 over Vx1. All right. This is our next important result, and I'm going to spend a little bit of time now talking about what this means. Okay, let's go ahead and discuss what this means for our set of particles. So remember that when this condition is met, we get two collisions per time chunk L over Vx1. All right, so let's go ahead and look at the simulator, and let's go ahead and just find what that distance is. I'm going to be generous here and just plug in the full 4 meters for my length. I'm going to ignore the particle size just so we can get like the upper bound for what this distance must be over. So if we take L equals 4 meters, my first particle, Vx1, has a speed of what? 1 meter per second. And my second particle, particle 2, has a speed of 0.36 meters per second. And so we're going to get that x1 is greater than, I'm just going to plug those values in real quick. We get 2.56 meters. Okay, so let's go ahead and just show that this is actually true in our simulator. If I put my particle, 2 meters works right here. So this is less than the 2.56 meter requirement. And so if I were to hit play, we would only get a single collision. Bam. Let's go back. We have a single collision at 3.64 seconds, right? The particle is far enough back for the first particle to ram into it basically before it runs into the wall. All right? Now let's go ahead and put it here at 3 meters. Okay? Or how about, let's go 2.8 meters. Okay, let's play it. We get a collision with the right wall. And then we get an immediate second collision following that. So we get 2 collisions over the course of our time chunk of 3.64 seconds. All right? So now we've kind of confirmed what this condition really means. Okay, let's go ahead and find an analogy between the 1-ball situation and the 2-ball situation before we go any further. Okay, when we had 1 particle in the box, right, we had 100% of the time, when the particle starts out here, when 2 time chunks go by, so this is 2 time chunks, right? The ball comes in and bounces off. Then 100% of the time, I could take this guy and multiply this by 100%. It would be the same thing, right? That's what really we're saying. That there's going to be 1 momentum transfer of 2 mvx into the right wall. That's what we're saying. So now for this guy on the right, what happens in 2 time chunks? For the guy on the left, 2 time chunks was enough to reset the ball. Okay? On the right here, what does 2 time chunks get us? Watch. Let's reset this. Okay. Play. 1 time chunk. And here we go. And there's your second time chunk right there. 2 time chunks is also the exact amount to reset the box basically in this situation. And every time at the end of the two time chunks, particle 2 is going to be in some more or less random location. And particle 1, of course, ends up on the left wall. Okay, are we super clear about that? If so, let's go ahead and write that down. So two time chunks goes by. And then things are going to loop around. We're going to have this particle with Vx1 again. And we're going to have particle 2 in basically some random spot. We're not exactly sure where it's going to end up, but it's going to have its speed Vx2. Okay. So now, remember before we defined this parameter, this x1, right? And it basically said something like this. Let's say that x1 is right here for our situation. So particle 2 is going to reset at some random position. We're not exactly sure where that is. But if particle 2 happens to be behind x1, we know that a single collision will happen with the right wall. Oh, whoops. Over the next two time chunks. And if not, let's just say else. So if it's past x1, two collisions will happen with the right wall over the next two time chunks. So the next thing that I want to clarify a bit is this little detail that now we're talking about two time chunks going by instead of one time chunk going by, and I'm saying that the same number of collisions happen. That's simply a fact that basically in the follow-up time chunk, no more collisions happen than just one time chunk going by. So here, if I run my simulation, watch the, let's pay attention to the time chunk. So I'm going to put the ball somewhere. All right, I hit play. All right, one time chunk, I get the one collision. And now watch as things reset. No more collisions happen. So two time chunks went by and I got the one collision situation. Let's go ahead and do the two collision situation. So we go 1 and 2. There's my one time chunk going by. But now watch, we're going to get no more collisions, right? So in fact, the whole thing that we were discussing before, where we were finding the number of collisions that happened in a single time chunk, that actually applies to the number of collisions that apply for two time chunks. Now, every time that our left particle loops around, once it gets back to its same spot, so bam, it's in the same spot after two time chunks, we're super clear on that. This right particle is basically in a random spot. It's really hard to predict exactly where this second particle is going to end up being. Let's see that again. Bam, and the right particle happens to be, over here. And we could keep repeating this, and we'd find that this second particle appears in more or less random spots after a set of 2 time chunks that go by, or every time that the left ball loops over back to the left wall. Okay? So with that noted, let's go ahead and say that this guy is in a random spot. Right? And we could consider it starting in a random spot. Starts in a random spot, and 2 time chunks later it ends in another random spot. However, I know that, let's say that it appeared on this side. And in this picture, this looks like it would occur about 60% of the time. Let's go ahead and call this situation X. If my particle happened to land before X1, oh, what do you know? I already said exactly what would happen. A single collision would happen. So we have some X fraction of our setups are going to result in the single collision. Okay? And for this guy, I guess I can do this in red. There we go. Let's call this situation Y, where our particle is after the X1. It looks like this would happen about 40% of the time, right? Just in this drawing. So, let's call this fraction Y. All right, let's put this all together in a very clear statement. The force on my wall, that average force, is going to be the change in momentum over 2 time chunks over 2 time chunks. We called this time chunk variable earlier just delta t. And this guy was equal to, let's just go back. What was the time chunk, remember? L over Vx1. Okay? And the change in momentum over those 2 time chunks seems random. We have 2 options. X fraction of times, we get the single momentum transfer, 2mvx1. And y fraction of times, we get 2mvx1 plus 2mvx2 as our momentum transfers. So this accounts for the single collision situations. And this term here accounts for the double collision situations. All right, let's write this out in one line. So we have x, actually we'll do it like this. So this, if we plug this in, this would be Vx1 over 2L times x times 2m Vx1 plus y times 2mvx1 plus 2mvx2. And let's complete this analogy. In this situation, we only had one momentum transfer, and it only happened 100% of the time, right? There was only a single situation that could happen. So, this would have just been times 1. And everything else lines up more or less exactly the same with our first situation on the left there. Now all we got to do is figure out what are x and y. And look at this. We can clearly see, based on how these chunks are labeled, it's going to be some ratio of x1 to the total length of our box. Isn't that beautiful? So our fraction x is just going to be x1 over L. And our fraction y is just going to be, because, these situations add up to 100%, it's just going to be 1 minus x1 over L. How nice is that? And now we just got to plug those guys in. Vx1 over 2L times x1 over L times 2 mvx1 plus 1 minus x1 over L times 2 mvx1 plus 2n times vx2. Oh, and whoops, it looks like I put that fraction bar a bit too far over. There we go. Okay, sweet. So now we just got to ask ourselves, well, what was x1? And we already calculated that guy. So I'm just going to go ahead and plop that guy in there. And now we just got to sub it in. Oh, it's getting exciting. This was a long problem, and now we're finally getting close to the end of it. And we're getting to that point where everything's going to start canceling, and we're going to be very, very happy. Oh, isn't this looking very nice right now? Let's go ahead and put some parentheses around this, just so that we know that we're expanding these entire two quantities. All right. L's are going to start canceling. Let's go ahead and start expanding these terms out. So we're going to get 2mvx1 minus 2mvx2 plus. Oh, and look at this. This is going to cancel with this one. And this minus minus is going to make this guy a positive vx2 over vx1. So all we got to do is expand this term out. And so we're going to get 2 times mvx2 plus 2mvx2 squared over vx1. And wow, would you look at this? This is going to be so beautiful. These guys cancel out with each other. And watch this. This vx1 multiplies over 2m times vx1 squared plus 2m vx2 squared times vx1. This 2l multiplies over 2l, over 2l. Now watch the cancellation. And also this was divided by Vx1. Here we go. Now watch the cancellation. 2's cancel. 2's cancel. This Vx1 cancels. The Vx1 cancels. And we get m Vx1 squared over L plus m Vx2 squared over L. Look at that. There's our result. It's literally just adding the time averaged force for each of the particles, like they were in their own separate box. Remember, this guy equaled 2mvx, or this guy equaled mvx squared over L. It's like we're taking two particles in their own separate boxes with speeds Vx1 and Vx2. We find the time averaged force on both of those, and we take them and we add them together. It's such a nice result. Now, I've seen a lot of textbooks that go from taking this result over here in the left, where we just find the time averaged force for one particle, and then just saying, for n particles, oh, we can just start adding them together. But I don't think it's intuitive, and I think you have to do this kind of thinking where you try to tackle this beast kind of actually thinking about the motion of these two particles and thinking about how you break your conditions down and go through, and you can find that result for yourself. If you want to, you could go ahead and repeat the same set of calculations for three particles. It's a little bit more tedious. You have basically multiple conditions now, and your fractions multiply together, right? Just like probabilities multiply together. But you could just as reasonably do it for that. But I really hope that this process has convinced you that for n particles, that the force on our walls would equal basically the sum from, let's go ahead and use I as our counting variable, from I to n of m, all our particles have the same mass, Vx I squared over L. And we can take the m and the L out because those are just constants. And we're just summing up all of the velocities squared. And this is what our force would look like for n particles. We'll go ahead and discuss this result more in the next video and organize it from there. But I just think it's so important to really take the time to consider this dynamical motion with the two particles. So, with that, thank you so much for watching.